Okay, here we go. Sorry about that. I was able to disable your efforts to sabotage things here. So back in business. Oh, okay. All right, so the product and quotient rules. Here's where we left off. Now, we could do that top problem. What would our approach be to that top one if we wanted to differentiate h of x? Yeah, expand it out, right? And then we'd get a polynomial and we could just differentiate term by term with our trusty power rule, right? That would be no big deal. Okay, there is potentially a slightly easier way to do that one, but it's 50-50 really. So there's not a tremendous need to be able to differentiate that as a product. But if you look at the bottom example, that is one that we cannot do right now. We have to have a new rule because we don't know how to deal with a function like this that is a product of two functions, right? The product of x, the function x times the function e to the x. That's not something we can handle. So that's what we're going to talk about today. Just myself saw the reminder I left for you guys yesterday. So the registration deadline is November 15th. Is anybody doing the AP test? Okay, totally up to you. If you decide you want to do the AP test, you have to just go in through your College Board account, and that's how you register. You sign up for the calculus AB test if that's something you want to do. Okay, I think I've told you it's not like you're going to be. This is not a dedicated AP class where we're going to have 6 weeks to do nothing but prep for the test and we're going to just scream through all the material. So it's not like this is really driven around the concept of everybody getting 5s on the AP test that's taking it. So it's up to you. I mean, I still think it's, if you do it, there's a pretty decent chance you're going to get credit for it, but it's kind of a little bit of a gamble. Okay, said that. So moving forward. The product rule. How are we going to deal with the product rule? So we want to build this, obviously in math, we want to build something generally. We don't want to build a rule that deals with this specific function, right? We want to build a product rule that deals with any product of functions. And so let's take the general product of f of x and g of x, where f of x and g of x are just random functions. Okay, does it make sense that if p of x is the function that we're calling this product, then by our definition of a derivative, this is the derivative of p of x? Stare at that and give me thumbs on that, up or down in a second. Does that make sense? That is our derivative. If we're going to rely on our limit definition of a derivative, which always works, it's just very time consuming. That seem good? Okay. This part right here, isn't that just p of x plus h, right? So p of x plus h minus p of x over h, the limit of that as h goes to 0 is the derivative, right? Okay, so this is a weird proof. I'm not going to dwell on this proof very much, but I want you to see some different approaches to doing proof. This is a really cool one, though. Here's something we can do that you don't often see. Let me go back a little bit. I built this carefully. Okay, kind of like that. Whoops. You know what? I don't think it's really going to matter. I'm just going to do this. Okay. So here's the weird step we're doing. Instead of multiplying by 1, which we almost always do, right? We've done that a ton in the past. We multiply by 1 in the form of, something divided by itself, but we do it in a tricky way where it's useful to us. This time we're doing the other operation that we can do, which is add 0 and not change something, right? I've got this expression for a derivative. I could either multiply that by 1 and and our expression would remain unchanged, or I could add 0 to it, and it's going to stay the same, right? Because 0 is the additive identity, just as 1's the multiplicative identity. Well, look what I did here. I just subtracted and added the very same term. Okay, but now I'm going to reorganize these terms, and I'm going to factor this in a way that's going to be a little bit tricky. Very cool proof. Did I not write the rest of it down? What did I do here? Did I not? Oh, I guess I didn't. Okay, so does anybody see a way I could do this and maybe factor some stuff out? You see a way we could do this? We could kind of push these things together. And what's my, my goal is to get something out where I'm able to factor some things out and kind of reorganize this. You see anything you could maybe do there? What if we were to rearrange these terms a little bit? So I did something like plus. I'm trying to think how this works myself here. If I factor it, I get G of that. Factor out. I want to subtract. I got to think just a little bit to myself here. Hang on. Okay. Okay, f of x plus h times. Okay, this. What if I take these two terms, this term and this term, and I factor out an f of x plus h? Okay. Is that going to work? Yes. If I factor out an f of x plus h from those terms, what do I get? F of x plus h times what quantity? Actually, I want these two terms. What am I left with if I factor an f of x plus h out? Okay. Okay, now what if I factor out a g of x from these two terms? What are you thinking?
Is the way that we're factoring, are we like separating because you know how you told us that we do the, like instead of slip and slide, sometimes you can do like not slip and slide.
Oh, okay. No, I see. I know what you're thinking. No, we don't have to do anything that complicated. We're just going to kind of rearrange, and this isn't such an immensely tricky thing to do, but it's just kind of it's something that maybe people wouldn't necessarily think of initially. So let's take the green stuff and let's factor out a g of x. Okay, if I factor out a g of x, what's left behind? Did I get that right? Yeah, that's going to work. Yep, that's good. All right. If I factor out a g of x, what am I left with? F of x plus h, okay, good, minus f of x. Yeah, okay, good. Everybody see that? And it's all over, everything is just over h, right? As h goes to 0. But now let's go ahead and kind of split this into some separate parts. Let's take this first, let's split this into two separate fractions, right? I've got this plus sign in the middle. Instead of writing it with a common denominator, let's write it this way. The limit of f of x plus h times the limit of the purple stuff all divided by h plus the limit of g of x as h goes to 0 times the limit of f of x plus h minus f of x over h as h goes to 0. Everybody buy that? And really, what did we do? So we split the common denominator, so we've got this fraction, but then this fraction is a product of f of x plus h times this quantity over h. Well, let's put the h with the purple one, right? Just like if I were doing something like this. If I had a times b all over c, I could write that as a times b over c, right? Okay. Now that ought to look pretty familiar there, some of that stuff. In the limit, as h goes to 0, we can probably skip this row. In the limit that h goes to 0, what is f of x plus h? F of x, right? So we end up with f of x times, what's all this purple stuff? What's that look like? The limit of g of x plus h minus g of x over h as h goes to 0. What is that? That fits a pattern, right? What is that? Looks like a derivative, doesn't it? Derivative of what? G of x, right? That's g prime of x. How about that? So we get f of x times g prime of x plus, what's the, well, we'll just bring the g of x down. Okay, we've got g of x times, what's that look like? This one right here. Derivative of f. Yeah, look at that. Look what we get. So the derivative of the product of f of x and g of x is f of x times g prime of x plus g of x times f prime of x. That's the product rule. So what's the moral of the story? Well, when you differentiate a product, it's just always going to be one factor times the derivative of the other plus the opposite. That's it. Okay. And here's how we usually write the product rule, something like this. Okay. You'll see it this way sometimes, but doesn't that look messy? If you write it using function notation, there's so many parentheses and brackets, and it just gets to be a mess. The derivative with respect to x of f of x times g of x is equal to f of x times g prime of x plus g of x times f prime of x. We just proved that. Okay, an easier way to write that is let's use u to represent f of x and v to represent g of x. We do this a lot in calculus because otherwise it looks so messy. So again, u is not a variable. U is meant to represent a function. Same with v. V is a function. Then the derivative with respect to x of the product of the functions u and v is just u v prime plus v u prime. That's, to me, is a way better way of writing it, right? Much more economical, much less messy, not so cringe provoking when you see all those nested parentheses, right? And then we can extend the product rule if we want to as products of as many factors as possible, and the same pattern holds. What essentially do you do with the product rule? If I have a product of a long string of factors, I get one term per factor, and each factor gets its term being differentiated, right? So we'd get, in this case, we'd get u times v times w prime, it's the w's term, plus u times v prime times w, it's the v's term, plus u prime times v times w, right? You see the pattern? And then we could have 10 factors if we wanted to, and we would just get 10 terms that follow that kind of taking turns pattern, and we get the extended product rule, okay? Give me 1 to 5 on that. Does that all make sense? So product rule is really a very easy one to apply. Let's do that. I mean, this one is no big deal. We can go back and do this derivative now. If I want to calculate y prime, what do I get? And by the way, because the terms are being added in the product rule, you can't mix it up. It doesn't matter which one you differentiate first. It really makes no difference, right? Because addition is a property that is commutative and associative, right? We can exchange the order in which we multiply things or add things, and we can change the order in which we group things if we're doing more than one process at a time. Like, if you see what I'm saying? But really, it's the commutative property we're interested in here. Those terms could be commuted and it doesn't change anything because they're being added. So take a swing at that. What is that? Everybody think about that for a second. What are we going to get? What do you think? Aubrey, what do you get for that? What'd you say? Not sure? Okay. Anybody want to take a poke at that? What's our, here, let's write it down up here. Let's write down the derivative with respect to x of uv. What's our product rule again? There you go, uv prime. That's supposed to be a v. Well, plus, there you go. Okay, so do that. U is x, I guess. V is e to the x. Okay. So if u is x, what's the first factor? X, yeah. V is e to the x. What's v prime? E to the x. Plus vu prime. So what's v? Right? V was the second one, e to the x. What's u prime? What's the derivative of x? 1, yeah. We don't even really have to write it, but I'm going to put it there just so we see that we're following that pattern. That's our answer. Y prime is equal to x e to the x plus e to the x. Because what's the derivative of e to the x? E to the x. Yeah, let's remind ourselves about those. From yesterday, because we just barely covered that yesterday. The derivative, see if you guys can remember these. These are just part of the ones, the basic ones. We had a list of a couple basic ones that we can just use now. We know the patterns. What's the derivative of sine x with respect to x? That was cosine, yep. Cosine x What's the derivative with respect to x of cosine x? Negative sine x. And then finally, the derivative with respect to x of e to the x is what? E to the x. Well, so that really was kind of a dirty trick for me. I should have probably reviewed these first, right? Now that we know those, though, we can take all of these plus our power rule that we know, and we can apply those with the product rule, and we can do all kinds of things we couldn't previously do. Okay, so we'll come back to that.
So E is the E in that equation is referencing the number.
Yeah. So what is the exponent? Gotcha. Okay, right. So this is the exponential function, f of x. Like if we're just to think about that exponential function for a second. Another exponential function would be something like g of x equals 2 to the x is an exponential function. So quick review from previous years. What is an exponential function? Instead of like a power function where I've got a variable base and a constant exponent, it flips that, right? With an exponential function, I've got a constant base and a variable exponent. So these are way more aggressive, aren't they, right? Because the exponent, as that gets big, these things get big really fast. You always hear the expression, man, that thing's growing exponentially. And what do we mean when we say that? It's explosively growing, right? These are the explosively growing functions, okay? All right, let's try one more for practice. How about you guys do this one for me real quick? How about if y equals, everybody try that real quick. Try that real quick. Just crank it out on some scratch paper. And then we'll talk through this one. Okay, well, you're doing that. Okay, let's take a look. Let's take a look. What'd you get? I started recording. Yes, I did. Thank you. So what do we get here? Okay, so we're going to say, we're going to get, oh, I forgot to unfreeze this. Okay, so, oh man, there we go. So we've got the product of two functions, x to the fourth times sine x. Just to keep things consistent, what I always do, I always just say, I start with the first times derivative of the second plus second times derivative of the first. It doesn't matter the order. So if we're going to do it that way, we would keep the x to the fourth the same, right? What's that going to be multiplied by? Cosine x. Plus what? Sine x times 4x cubed, right? Does that make sense? Okay. And then we'd probably want to rewrite this. This is kind of a sloppy way to leave it. We always want to put stuff in front of a sine function so there's never any confusion about what's inside the sine function and what's not, right? So we would rewrite this as x to the fourth cosine x plus 4x cubed sine x, like that. Okay? That'd be fully simplified, very pretty form. Okay, so now what about quotients? Well, we can do something similar for quotients. And I'm not going to drag you. You guys have done, you put in your proof time today. I won't drag you through the proof of this one. But here's the pattern, right? This is our quotient rule. The derivative with respect to x of the quotient of f of x and g of x, so f of x divided by g of x, is equal to g of x times f prime of x minus, that's important, minus f of x times g prime of x divided by g of x squared. Okay, this time we're subtracting, and subtraction is not a commutative operation, right? 3 minus 5 is different than 5 minus 3. So now you have to actually remember this properly because the order is important. It's easier to think of with u's and v's. The derivative with respect to x of u over e is just v u prime minus u v prime over v squared. So how do you remember that? Which one do you multiply and which one do you divide? This way, just this little song or this little sing-song saying here. Low D high minus high D low. Everybody say that. Low D high minus high D low. Okay, better say it one more time. Now you'll never forget it, right? And the way I actually do it, like this is, I don't remember where I heard this one from, but I never actually knew about this when I started. When I started teaching calculus, I'd never heard that little saying. I don't know how that one escaped me. But the way I always taught my students in the past is you start it off, it sounds like video. Whatever sounds like video is the right way. So it's V du d, right? U prime is du dx or something, right? So V du dx, that sounds like video. So that's how you know you're doing it right. Okay, question. What does low d high mean? Because u is the high function, v is the low function in our quotient, right? So you do low by itself times d high minus high times d low, okay? Where high is the numerator, low is the denominator. And it's always divided by denominator squared. Okay, so there's our pattern. Let's practice this. What about something like this guy? Okay, now this is one that we cannot do right now without the quotient rule because I can't simplify this and write it as a power rule. Okay, so we have to use quotient rule. Okay, so what are we going to get here? As you've already seen, I make the red factors the derivatives just so we're always consistent here when we're using these rules. So help me out. Low d high minus high d low. What's low here? Okay, good. So we get low is x squared plus 1. What's d high? Derivative of the top, which is, no, that's derivative of 5x is what? What's the derivative of 5x? 5. Okay, so high is the top one. If I differentiate the top, I'm going to get 5 plus 0. Derivative of a constant is 0. Everybody agree that d high is 5? Okay, so there's low, d high, minus, what's high? D low. Oh, me. It must be so entertaining for you guys, just endlessly entertaining to watch me up here, this big buffoon up here, just stumbling through things, pulling up the wrong tools. Okay, that makes sense. Low D high minus high D low divided by what? Bottom squared. Okay, so now we've got to have the quantity on the bottom, x squared plus 1 quantity squared. Calculus is done. Often when you're doing calculus, the calculus part, differential calculus, and I need to duck because you're going to throw things at me here for a while when I say stuff like this, but differential calculus is easy. Integral calculus gets a little harder. I had to duck that one. And you'll think the same thing soon because differential calculus, when you're taking derivatives, you're just following rules. It's a little more complicated when you're doing the reverse of that, when you're trying to anti-differentiate, which is the second part of the class. That gets a little trickier. But this is really, you memorize some rules and you follow the rules. And there's some steps there for sure. But my point is that most of what you do in differential calculus is not the calculus, it's the stuff that comes after that. It's the algebra. Now we got to clean all this stuff up. A lot of what we do is cleanup, algebra cleanup. So how are we going to clean this up? You're going to get so good at algebra. You'll come out, you will just be algebra machines at the end of this year. How do we clean that up? Now you know what to do. What do you do here? What do I do to the first? Yeah. Okay, I could expand now. Okay, now here's something. Expand the bottom. That's a logical step, and that's exactly what I would have said if I were sitting out there. But we're not going to do that. We want to keep the bottom factored for reasons that will become clear later. But the top needs a lot of cleaning. What do we do on the top? Yeah, good. We expand the whole thing out. Distribute the 5, distribute the 2x, combine like terms, right? So on the top, we're going to get, if I distribute the 5, I get 5x squared plus 5. Now let's distribute the minus 2x up here. What am I going to get? Minus 10x squared, good. What's the second one going to be? Plus, because I'm going to do a minus 2x times a minus 2. Does that make sense? Plus 4x? Okay. All divided by, we're going to leave the bottom factored, x squared plus 1 quantity squared. And on the top, now if I combine like terms, I get what? Negative 5x squared plus 4x plus 5 all over x plus 1 quantity squared. Is that going to factor? Let's see. Oh, x squared, you're right, yep. Let's see, I'm going to get numbers that multiply 25, add 4. No, that one's not going to, okay? Top doesn't factor, okay? So we're done. That would be our function in simplified form. It's a mess, but we don't care. That is the derivative function. Why do I need a derivative function? To find values of the derivative. I could plug values of x into that. That's not that big a deal, right? Make sense? Okay, are we out of here in 1 minute? Okay, good place to stop. We'll practice some more of this tomorrow, and then you guys ought to maybe even have maybe a little time to work tomorrow too.